So this video is just me going over worksheet 2 pie chart practice. So I'm going to start with number 1. So number 1 is meant to show a jumper just before he leaves the bungee platform, and then it's meant to show him just as he is about to spring back up into the air. So the system is the jumper, the bungee cord, and earth. Okay, remember, we always want to include earth just to make sure that we are including everything that we need to include within the system, but you also want to specifically include any items that are very obviously in the system, okay? So we have the jumper here, and he is just standing here. So he has 100% gravitational energy, okay? This is because he is very up high within the image, and he is about to jump. The second, the bungee cord is stretched to its limit, and it is about to spring back up into the air. So this would be 100% elastic energy, okay? So he's not meant to have any kinetic energy during either of those. Okay, so here's the second one. So for the second one, we have a pendulum that's swinging back and forth, back and forth. And these pie charts actually look a lot like the pie charts from the skater park that we went over last class, okay? So at each maximum height point, he has 100% gravitational energy, because there is a split second where at the very peak of that motion, he is standstill and he is just about to fall back down. The equilibrium point here is the lowest point within the actual sketch, and he is about to swing back up towards the maxima point, okay? So at this point, he is 100% kinetic energy. And then here, kind of in between the maxima point and the equilibrium point, he has a little bit of gravitational energy and some kinetic energy. Now we've added a higher percentage of kinetic energy here in B because this location is not really like dead center between the equilibrium point and the maximum point, okay? So because it's closer to the equilibrium point, we have more kinetic energy than gravitational energy. Okay, moving to the second page. So we have a student starting on the first floor, climbs up the stairs to the third floor, and we want an analysis for each floor, okay? So this is assuming that we have a system which is the student, the stairwell, and earth. Also, we are assuming that at each location he is standing still. So we are assuming that they are standing still, which is why we have no kinetic energy within this. If you were assuming that there was motion, like it was a snapshot while he was moving, then I think that's fair to have some kinetic energy there. However, I'm just assuming that there is no motion here. So on the first floor, we have 100% chemical energy, okay, because we are a human being doing work. Humans use chemical energy to do work. As we go up to the second floor, we still have quite a bit of chemical energy. Our gravitational potential energy has gained, and also our dissipated energy has also gained. When we move up to the third floor, we have a lot more gravitational energy, and we have lost some of our chemical energy, and we have also gained our dissipated energy. Again, your percentages do not need to look the same as this. We are looking for overall trends. So overall, we want to see an increase in gravitational energy. We want to see a decrease in chemical energy, and we want to see an increase in dissipated energy. Okay, so for number 4, we have a space shuttle starts off on the launch pad platform at Kennedy Center in Florida and then blasts off into orbit. Give a pie chart analysis for the shuttle before launch. Okay, so this is before launch. We just have 100% chemical energy. Okay, the chemical energy and all that jet fuel. During its rise, so during the rise, we are losing chemical energy. So our chemical energy is decreasing. We are gaining height. So our gravitational potential energy is increasing, and the chemical energy that we are losing is also going into dissipated energy. Then we are finally in orbit. If you are in orbit, you're just kind of orbiting around, okay? And we have half dissipated energy, half gravitational energy, just kind of assuming that we are moving. The thing that is keeping us moving is the gravitational energy, okay? Again, I haven't included kinetic energy here. If you had kinetic energy in here, I think that's also a rational thing to have during rise and orbit, but neither of those are in place within this key. Okay, but if you kept that there, I think that's rational. The big things I would be looking for here, though, is a decrease in chemical energy and an increase in dissipated energy and an increase in gravitational energy. Number 5 is a wind-up toy. So we're starting with A down here and going up. Any wind-up toy that we have is always going to be based off of elastic energy, because as you're winding it up, we have elastic energy. Okay, so at the beginning, we have a little bit of we have a lot of elastic energy, and we have kinetic energy. Our kinetic energy, you'll notice, will be constant throughout. Okay, so if you look at all these pies, it's going to be exactly the same. The thing that is decreasing as we move from A to E is we are decreasing in elastic energy, we are increasing in dissipated energy, and we are increasing in gravitational energy. Okay, because we are moving up an incline, meaning we are going to gain altitude or gain gravitational energy. We are moving at a constant speed, so we have kinetic energy is constant, and as we are but we are still have some dissipated energy because we are losing that elastic energy as we move up. Then finally, down here, the final one is the stick of dynamite. Dynamite is not a atomic weapon, so that's why we have 100% E chem here and not E atom. Okay, it's saying that it blew up in an empty part of the desert, doing no damage. So if there was no damage, all of that energy just kind of dissipated, which is why we have 100% dissipated in the second pie.